All right, so our problem of a jet airplane flying with a constant speed along a straight line during its ascent. It's ascending at an angle of 30.0 degrees above the horizontal. The plane has some weight, which has a magnitude of 86.5 kilonewtons. And its engines provide a forward thrust along the line of the aircraft of 103 kilonewtons. In addition, the lift force, which is perpendicular to the wings, lift force is always perpendicular to the wings, and the force of air resistance are acting on the plane. Air resistance, of course, would be directed opposite the motion of the aircraft. All right, so let's draw a picture of this aircraft. Instead of drawing the aircraft itself, I'm just going to go immediately to the free body diagram. Right? I'm going to immediately, and this immediately to me sounds like a question about forces and Newton's second law, because I'm given no quantities of motion here except constant velocity. All right, so first I'll start with our free body diagram. All right, we were told that the angle of attack of the nose of the aircraft is 30 degrees above the horizontal. Okay, so that would be the direction that his thrust is oriented. Okay, there's the thrust. I'll label that with T, which we know the thrust is, I think it was 103 kilonewtons. Right, so there's our thrust. We also know the angle of that thrust. It's in the same direction as the nose of the plane, 30.0 degrees above the horizontal. All right. Directionally opposing the aircraft would be drag. All right, so drag must be pointed directly the opposite direction. Okay, so I'll draw this way. Okay, draw that way. Here's our drag. We know the lift force is perpendicular to the plane, to the aircraft. So that would be, here's perpendicular. If I find this is my horizontal line, I need to draw perpendicular to that. That would be my lift. Okay. Here's my lift. I should label these as well. Lift. And this here is my force due to drag. Right, and the last force that I have not included here would be the fact that this aircraft has some mass and therefore some weight. So we'll draw the weight of this aircraft straight down. All right, so here's a reasonable free body diagram for our object, for our aircraft. All right, now to know what I'm going to do with this, remember first we said, well, this immediately seems like a forces kind of problem. Immediately seems like forces or Newton's second law application, something there. Because I'm given no motion quantities except one. I am given one motion quantity, and that is constant velocity. Constant velocity. All right, if we're moving at, oh yes, then again. Constant velocity would mean if it's moving at 10 meters per second 1 second, then the next second it's also still moving at 10 meters per second.
That would be the 0.3.
If you said 0.3 kilonewtons, newtons would be a measurement of force. Velocity would be measured in meters per second, or some distance per period, some period of time. Right. But when I see constant velocity, I have a key term immediately come into my head, which would be equilibrium. Equilibrium, which means that the net force in the x direction is equal to 0. The net force in the y direction is also equal to 0. Right? Not accelerating, we're moving at a constant velocity. All right. For all of these two-dimensional problems, now that I know, okay, it's a problem in two-dimensional forces, I know because I've been told constant velocity, I'm thinking equilibrium, so I have to say, all right, if I look at forces in x, I should find 0. If I look at forces in y, I should also find 0. Right? This is just like our Joe's sign problem. Except with the Joe sign, the velocity was constantly 0. Here, for a jet aircraft, it's constantly something, right? But as long as that something, some velocity is still constant, then we have no acceleration. And so because we have no acceleration, the net force must be 0, right? And that's why we said equilibrium, because it's the state in which the net force on an object is 0, which would occur because of a 0 acceleration. The acceleration is equal to 0. That implies the net force is equal to 0. All right. So we'll tilt our head here to where now this is our x-axis and this is our y-axis. So x is along the angle of attack of the aircraft, and then y is perpendicular to the aircraft. Right? We actually don't have to do that. You don't have to. You could solve it differently. You could keep it where where the x is the normal x and y is the normal y. We normally tilt the axis because it's typically easier to resolve the problem if we tilt the axis. Because notice if we don't, then we have 1, 2, 3 vectors that are in 2 dimensions. The lift, the thrust, and the force of drag would be in 2 dimensions. If we tilt the axis, however, how many forces do we have that are acting in 2 dimensions? It would just be the weight. This would be along the x-axis, thrust is along the x-axis, and lift is along the y-axis. So it's to our advantage to tilt the axes a little bit, and it simplifies our problem. Okay? So now all that's left is, this is the real fundamental physics idea. There's the only little bit of physics left is to say in which direction is that force oriented. Otherwise, after this point, and after we rotate the axis, most of this just becomes a math problem. And applying the more complex trigonometry, or at least complex to y'all at this point in your trigonometry careers, applying it to this problem. All right, so if we look at forces now along the x-axis, okay, we have thrust is along x. We have force of drag that's also along x in the negative direction. Lift is not in x at all. It's completely in y. Weight, though, has a little bit in the x dimension, and it would be down, right? The weight of our aircraft wants to bring us down along that line and a little bit down towards the Earth. Right? There's our weight in y and our weight in x. So we also have weight in x. Those are our 3 forces that are acting on our aircraft in the x dimension, in our new x dimension. We can do a bit of analysis there. Thrust is positive x, as long as I say this is positive, and that's negative. Okay. Drag is in the opposite direction of our thrust, minus drag. And then weight in x is opposite, or is in the negative direction. All that has to equal to 0. Okay. This is our fundamental equation when we assess the forces that are acting on our aircraft in the x dimension. And we should go back at this point because good analysis so far, but I need to figure out why do we need to know this information. So I need to remind myself. Is we're trying to find the lift force and the drag. Okay, lift and drag force. We've been given the thrust, so I know thrust. The thrust again is 103 kilonewtons. We've been given the weight of the aircraft, I believe. Yep, we have the weight of the aircraft, 86,500 newtons, or 86.5 kilonewtons. Okay. So if I know the weight, then I can find weight in x, right? This 30 degrees there is the same as the 30 degrees here in that little angle. So we're trying to find force of drag, so I can isolate force of drag in this equation. Again, this is just math now, right? The physics for sum of forces in x is already done. So I just need to get this guy by himself, so I'll say tension minus weight in x equals force of drag. Okay. I'm sorry, I said tension, it should be thrust. So our thrust is 103 kilonewtons. Okay. Our weight in x, let's see, to get x, we're going to have to use sine here, right? Because that's the vector that's opposite of our angle of 30 degrees. So it should be whatever our weight is, the magnitude of our weight, right? Our resultant weight, which is 86.5 kilonewtons. 86.5 kilonewtons. Do we remember what a kilonewton is? Just like a kilometer would be 1,000. So 1 kilonewton is 1,000 newtons. Okay. Times, what did we say again? Sine of 30 degrees. Okay. Sine of 30 degrees. This all together. Okay. And that equals my force of drag. There's my force of drag. Okay. So we found the force of drag. We look at forces acting in the y dimension. And while I'm working this next part, can somebody give me the calculated answer for this right here? Remember the kilonewtons, that should be 103 times 1,000 would be 103,000 newtons. But we'll look at forces in y. Forces in Y, let's see. So I look back at my free body diagram. I have lift, all right, that's one force that's acting in the Y dimension. And the only other force acting in my new Y dimension that's perpendicular to the axis of the line of attack of the aircraft is weight in Y. Okay. In other words, a good physical way of thinking of this is the lift is having to completely support the Y dimension of the weight, right? That's what the lift is supporting, the Y dimension of the weight. That has to equal to 0. Just like up here, this had to equal to 0. Move this up a little bit. So these two must be equivalent to each other. Those are our only two forces that are acting in the Y dimension, with our lift pointing upwards and our weight in Y downwards. So our lift must be equivalent to our weight. We know that our weight in Y is, this time, weight times cosine of 30 degrees, so 86.5 kilonewtons times cosine, right? Because that would be the adjacent side here. Here's our adjacent side. Okay. Adjacent to the 30 degrees is weight in Y vector. So times the cosine of 30 degrees. And that should be what our lift force is. I think for my, I should get 59.8 kilonewtons of drag. 59.8 kilonewtons of drag, or 59,800 kilonewtons. And then my lift should be 74.9 kilonewtons, or 74,900 newtons of force. So when you're traveling on an aircraft, these are the forces that are happening to you as you go up in an airplane. You have 4 fundamental forces that are associated with any aircraft. You have the thrust that's moving it forward. You have drag that's opposing its motion through some fluid. You have the lift force that's taking it off the ground. And then you also have the weight of the aircraft because it has some mass. Relating all those forces together in this problem using Newton's second law, we can find what the force of drag if we know the force of thrust, and we can find the lift if we know the weight of the aircraft. All right, any questions on this problem?